Hey, welcome back. Time for a couple more applications of double integrals. Um, we're going to build on the idea that we had from the last video about probability density. Let's say we have, and the key word there is the density of an object. So let's say we have some two-dimensional object. Now this could be a really thin object, I mean not actually two-dimensional, but really, really thin. But we could imagine that we have this object, and what we're going to do is we're going to talk about this object, and we're going to talk about either the charge of the object or the mass of the object. So a two-dimensional sheet is often called a lamina. And so situation one is that we have a two-dimensional object, so a lamina, that has a charge on it. All right, so maybe we've got some different things happening in different places. Maybe there's some positive charged things, maybe there's some negatively charged things, but the idea here is that there's a different amount of charge on different parts of this lamina. And our goal would be, let's figure out how much charge there is on the whole thing. So if all of these little bits of charge, all kind of the pluses and minuses canceled out throughout, and then we just spread them out over there, what would be the total charge on it? So we're dealing with this situation where we have this two-dimensional object. It has a charge on it, where the amount of charge density depends on the location of D, location in D. So if we were going to write that mathematically, what we're saying is that there exists a charge density function and we're going to write that as sigma of xy. This is sigma, Greek letter sigma, that says how much charge per unit area there is at a point xy in D. So at any point here, we would say, maybe over here, we would say the point has a negative charge density, whereas over here we would say the point has a positive charge density. And so we're using our basic principle that if we're trying to calculate how much charge there is on the whole lamina, well, we're going to add up all the little bits of charge throughout the whole lamina, chop it up into little bits. So if we're going to calculate this, how do we do that? Well, we're going to say, well, how much little charge is there in a little area? Well, we're going to integrate over the whole domain of this charge density times dA. All right, what is this? This is charge per area, and this is area. So this sigma xy times dA is equal to the dq. So when you have a charge density function, or an anything density function, then you can take the integral of it with respect to x and y, and that's going to give you the total charge. Similarly, you might feel even more comfortable talking about this. We have this lamina here, and in this lamina, maybe you've got some denser material over here, and then you've got some less dense material, some more dense material, some less dense material, and so there's some density, there might be a mass density going throughout. So similarly, if you have a lamina with a varying mass density function, and in this case we won't use sigma, we'll use rho, another Greek letter, rho, then what we have, similar to up here, the mass of the object is the integral of a whole bunch of little bits of mass. So that's going to be double integral over our domain of our mass density function, dA, because now instead of charge per area, we have mass per area times area. All right, the last thing that we could talk about is what happens, like we have this region that has mass. We might want to figure out where we should put our finger underneath the mass, this object, in order for it to balance perfectly on our finger, right? So since this object is heavier here, but much lighter over here, then the center of mass is probably somewhere around here. So let's be a little bit more careful about that. So one last application is to find the center of mass of a region. To do this, we determine the average value of the mass function, the mass density function. But one thing we need to keep track of is we're going to weight it, so the mass density function that is weighted by its x component and then independently by its y component. So that is the center of mass is calculated by, you take the double integral of x times the mass density of xy dA divided by the mass as the x coordinate, and then you take you integrate y times the mass density dA divided by m. So what we're doing here, let's do an example here where, let's say we have a one-dimensional object here. And in this one-dimensional object, we have 3 units of mass here. We have 1 unit of mass here. We have 5 units of mass here. We have 2 units of mass here, 2 units here, 1, 1. So we have an object here that's super heavy on the right-hand side and super light on the left-hand side, and super light on the right-hand side. And so if we put this in coordinate systems, then we're taking our mass density here, and we're dividing out, and we're multiplying by the x-coordinate in this system. So we'll write 3 times 1 plus 1 times 2 plus 5 times 3 plus 2 times 4 plus 2 times 5 plus 1 times 6 plus 1 times 7. So what does that get us? 3 plus 2 is 5, plus 15 is 20, 28, 38, 38 plus 13 is 41. And then we have to divide out by the total amount of mass. And so the total amount of mass is 3, 4, 9, 11, 13, 14, 15. 14 out of 15. And so 14 out of 15, that's a little bit less than 3. So that's less than 3. So what that's saying is that the center of mass of this object is located over there on the left side, as we would expect. And so when we're dealing with an object that's in 2 dimensions, well, there's a certain amount of mass we have to find. We're basically finding the x-coordinate independently of the y-coordinate of the center of mass. And if we have an object, so if we have an object, some geometric object, and we're looking for the centroid of the region, we can assume that our mass density function is equal to 1. So this formula becomes that the centroid, so this was the center of mass, and the centroid is what happens when we integrate x dA divided by the area, and we integrate y dA divided by the area. All right, so that means that if we have maybe a triangle here and we'd like to figure out where is the centroid of this region, we can set up our integrals over this triangle, figure out the integral of x dA divided by a, the integral of y dA over a, and that's going to give us the x-coordinate of the centroid, and it's going to give us the y-coordinate of the centroid. All right, let's stop here for today. See you later.